So I'm talking to you today about crypto agility and what needs to be done to immunize processors against the exploitations that will come as a result of trying to enable crypto agility on RISC-V systems. So first, a quick thing on what crypto agility is, what we mean by it. This is the concept of designing your system so that you can support multiple cryptographic primitives and multiple cryptographic algorithms at the same time. And you want to be able to do this by supporting multiple combinations of primitives or algorithms so that when vulnerabilities are discovered, you can switch to different combinations of algorithms and primitives in a at least partially automated way. One of the reasons this is becoming important right now is if you're designing hardware SoCs for global distribution, there are starting to be some rules in place about what cryptographic algorithms you can utilize in different regions of the world. And what some of the big vendors are noticing is that in order to prevent having to have multiple SKUs, multiple parts that are shipped to different parts of the world and having to manage the logistics of that, they need a way to be able to have a crypto agile system where they can deploy different algorithms and primitives to different parts of the world by using the same SKU. There's other reasons that crypto agility has been getting some headline news recently. There's been advances in computing technology, so the computers are getting faster and it's causing cryptographic keys to get much larger in order to remain secure over long periods of time. A way to combat that is to be able to change your keys, deploy them, and be more kind of agile in your smaller keys. There's concerns about quantum computing, having the ability to break crypto algorithms relatively quickly in the not too distant future. There's a prediction by Gartner that this could happen to 2048-bit RSA between 2025 and 2030. And NIST is predicting that public key cryptography will be quite vulnerable to quantum computing. Historically, what we've seen is that there are typically latent defects in cryptography algorithms that severely weaken their effectiveness. This has happened to RSA, to SHA-1, to MD5, to DES. And so you can extrapolate from there and say, whatever algorithm you've got today, there's probably going to be some kind of flaw exposed over the life of your product, and you're going to need some way to remedy that flaw. Typically, that means deploying some new algorithm to get past it and keep your device in service. So for embedded devices, what does this all mean? Typically, the most cost-effective way to affect crypto agility is to move cryptography to software. This is, in recent history, over the last decade, become something that's actually reasonable to consider. We moved to hardware accelerators for cryptography due to power, due to performance and latency requirements, but processor cores have gotten fast enough that doing cryptography in software is once again a decent option. However, doing that brings its own risks. Cryptographic software itself could have bugs, which could lead to more vulnerability. So now you have not only the vulnerability and the bug inherent to an algorithm that could be flawed, but the implementation of that algorithm itself could have software bugs. In addition, you've got other software that's running on the processor that might expose vulnerabilities or expose the cryptographic algorithm itself, or compromise the keys that it's using or the intermediate data that it's processing. So that even as secure and as correct as your cryptographic software algorithm may be, the fact that it's running on that system could expose your data to other software running on the system. This could be true through side channel attacks, through memory leaks, through software exploitation. So to enable this concept of running your cryptography in software, you need to make sure that your embedded system is actually secured and safe. And what that means is you have memory safety so that you can avoid and prevent the exfiltration or subversion of the encryption software. And this can include completely skipping encryption, right? A software-based attack that attacks control flow, that while you've got unencrypted data resident in the system, completely skip the encryption call and cause the system to ship out the data unencrypted. Data privacy needs to exist to protect the key material itself. Data integrity needs to exist to secure any update mechanisms. And of course, today we all know about side channel protection. You need some way to secure the information regarding the physical implementation of security. One of the things that's kind of key to remember here when we're talking about security in the embedded space is, in order for crypto agility to work and be something that can be in software, one of the key things you need to have is the ability to update that algorithm through some kind of network channel. And so even if you have a secure environment to run your cryptography, what you have to be worried about still is the whole supply chain of that update getting down into your deployed devices to update your algorithm to something new in the future. And so there's a couple main approaches that could be considered in order to secure your system for being used by such sensitive algorithms. One, and this is used commonly a lot today, is to use a dedicated processor subsystem. This does a good job of hiding the algorithms and the immediate data, the intermediate data, and the keys from other software. However, it's likely a much smaller and less powerful core than the main application processor. So you're still carrying large crypto accelerators with you to do this. It's typically more costly to put down a high performance processor than it would be with existing accelerators. And you have to have, for it to be agile, you have to break your accelerators into lots of smaller, multiple primitives, which may or may not actually be much smaller than what you had before. In many systems, this additional dedicated processor system will remain idle and unusable for other workloads. So you're just kind of basically carrying some leakage, carrying extra silicon area and cost. And like I was saying before, you still need to be able to update that crypto software, typically through your main processor, through an update channel. And so you still need to worry about the integrity of the algorithm that's getting updated and the integrity of keys and the update in that whole channel. The other approach, of course, would be to secure the main processor system. When you do this, you get to use the fastest processor on your chip to run your crypto software, which is often time sensitive, latency dependent. You can load balance with other workloads without having defined hardware boundaries. And you can secure the update process kind of inherently in that design. So there's a few approaches to how do you secure a main processing system. One approach that's getting talked about a lot recently is to use machine learning AI algorithms to determine what a typical behavior profile looks like and detect some anomalies. These can be behaviors that are detectable via bus traffic, power profiles, electromagnetic interference, thermals, on many other signatures. This typically requires some dedicated hardware to capture that information. It requires software running somewhere, typically on that main system, to run the algorithm that's doing the profiling of those signatures. This type of approach suffers from false positives and false negatives because it's a heuristic type approach, and it's not actually able to identify the point of the vulnerability. Instead, it detects a symptom of something having gone wrong rather than the initial cause of the problem. In addition to that, you still have a dog fooding problem of how do you protect the software whose job is to protect the software if that software is also running on the same device. There's also the concept of virtualization, where you can split your processor, your heavy-duty main workhorse processor, into multiple virtual processors and create compartments between them to run the cryptography algorithms in one section that's protected from all the other software threads on your device. This can do a pretty good job of protecting the software from the other threads. However, you still need communication channels to exist. And so you can still have API level vulnerabilities between the update mechanisms and the cryptography software that's running in that kind of virtualized environment. And the other thing to keep in mind here is there's typically only so many virtualization layers you can put in. Today's systems, you have 2 or 4 typical work zones of virtualization you can have. There are some out there that can create many more zones, but you still have to worry about all the messaging channels that would be between those zones and all the other threads, and what that API looks like, and what types of attacks can funnel through that API. And then there's another way that you can secure a main processing system by inspecting metadata on the software that's running all the time. You can use metadata on instructions and on data to define and enforce correct behavior of software. You can define things like memory safety, prevent any and all buffer overflows on the stack, on the heap, on globals, on local variables. You can enforce data privacy, you can enforce data integrity, you can prevent data-oriented attacks by enforcing standardization. You can prevent code injection attacks with stack frame protection and control flow integrity. And furthermore, when you do something like metadata tracking, you can precisely identify the vulnerability under attack down to the actual PC of the attack. And you can report that attack vector up to your communication chain and get an update to fix it through your secured update and secure root channels. So the point that I'm making here is that with the principle of accelerating change, technology is going to continue to advance, cryptography is going to continue to get defeated, and that's going to further demand this concept of crypto agility. Crypto agility is often going to mean cryptographic software. And software, as has always been true, is going to continue to have flaws. It's going to continue to have bugs that can be turned into exploits, exposing those embedded systems and those cryptographic algorithms and data. And therefore, your embedded system needs to have a secure, high-speed processing system, which would be a much better option than a separate, low-speed, dedicated cryptography subsystem on your device. You really want to strive for securing that main processing system in a precise and updatable mechanism. And that's everything for me.